randomness extraction. And randomness extraction is one thing that stands in the process of creating random numbers. So basically, when we're talking about random number generation, it's a black box that spits out typically ones and zeros that are equally distributed and not correlated. Not correlated, that's a word that doesn't make it feel uncomfortable. Right? Cool. Great. So, independent or equally distributed zeros and ones. It's not hard to get something that spits out random ones and zeros. The simplest way is to get coin and flip it, or to make an unstable electrical circuit, or you name it. Can you add something?
Temperature sensors.
Cool. Yeah, absolutely. The noise of the analog to digital converter in the less significant bits. Yeah, absolutely. The problem here is that it's not often that the distribution that we get from this very process satisfies the distribution condition. So typically we get a certain distribution. We want it to be zeros, ones, 50%, 50%. And it is often that we get something like this and this. When one of those, hi, nice to meet you. There's a free seat here. You're welcome. And that's one of the best case scenarios, because what we usually get is not a discrete but continuous distribution, where when some of the values are more probable, some are less probable, and we get the whole continuous spectrum of this is not the most correct way to use the term spectrum, however, the whole continuous range of values with all of those probabilities. And we want its probability and its value, the random value that we are measuring. And we want this thing to be somehow converted into this thing. That's probability, and trust me, it should be the same and not like the one I have on X. Now, so the very process that stands here is the randomness extraction. That's the most inexact definition of randomness extraction you can get. And there are true random number generators and pseudo-random generators that are typically spoken of when we're talking about random numbers. I don't think you need to explain to be explained how to distinguish what's the difference between true random numbers and pseudo-random numbers. Do you?
Let's try to define it. I have some understanding of it. Like
okay. So typically, when we need a random number, let's say we are in our desktop environment and we need to get some secret keys generated. We ask our operating system for certain this number of this length of random numbers. Operating system gives us this very sequence immediately, but those numbers are typically produced by a special function. The special function that has one seed f of x and then f x. And this function, once being seeded with something random, will make an infinite sequence of pseudo-random numbers. Those pseudo-random numbers are distributed equally, and those are hard to predict. But once you seed this very function with a certain seed, it will always be the same. So if you feed it random seeds, then you will get random results. But same seeds result in same sequences. So this thing is called pseudo-random number generator. And true random number generator is basically the one that very idiotic. So a true random number generator is the one that gives you just the true random numbers without any asterisks and additional conditions. Okay. Examples of sources we have already mentioned. There can be actually any event like time between the car passes on the streets, or like the ones used in our Linux and most likely Windows environment as well, are the input events that are produced by humans. Those are considered random because those cannot be predicted, and those are always unique. Once you boot up your operating system, you enter a password, and the time differences between your keystrokes are always unique, and hence those are considered true random source. The true random source with certain distribution that needs to be straightened up into this very flat distribution. So those are examples of sources. Same goes to mouse movements, and as far as I'm concerned, currently network activity in local area network is also considered random enough to be fed into a random number generator of a Linux operating system. You may correct me if I'm wrong. Okay, so can you just looking at those examples, introduce a certain function that would straighten the distribution? What? Average. Okay, so could you explain us? We get 0, 0, 0, 1, 0, 1, 0, 0, 0. What do we do to get something from this sequence?
So we should get number of this number once, then we should take the average of these numbers and go one by one. This will be we go number by number, like flip every second. Flip every second 0 because there are no zeros or ones.
Oh,
not every second.
At the time we want to exclude this thing. Yeah.
I couldn't get it. We are translating now real numbers from this curve distribution or what?
Let's suppose we have this very bad source of randomness with high probability of zeros and low probabilities of
I got it.
ones. Okay. Yeah, and it gave us this sequence, and we want to get random number of numbers. So what would be the most stupid maybe way to get something random from this? Can we get one random bit from this sequence?
Do you mean like
we can take
from
any
each distribution.
Uh,
So we have like a source, random number
Yes.
generator, and
so the distribution is the following. We have
Yeah.
high probabilities of zeros and low probabilities of ones.
If you want just a random bit, we can take the first one because it's also random.
If we take the first one, then over here we will get the same distribution with high probabilities of zeros and low probabilities of one. Can we get something that?
of course we can sum it up, and it would be it would probably have Gaussian distribution, no?
Okay, it
correct.
smells like central limit theorem, right?
Yeah,
Cool.
that's it.
But the sum is not binary. Can we make it binary?
Yes. If you just get more or less around 1 digit.
Could you please rephrase it in a different way?
Yes, you could get some of these bits and just get numbers maybe more or less around 1 limit.
Okay. So we expect a certain average, right?
Yes.
And we want to compare if the sum is more or less. That would work. Yeah, that would work. That would require the knowledge of this very distribution and hence the average. Yes, and that's a valid randomness extraction procedure. However, in a more programmer-like way, it could be very easy to just, for example, XOR all of those things, and that would be a random value. Another example of an extractor. I don't know if you are familiar with cryptographic one-time use notepads. No?
Oh, yeah.
Okay. So the idea is the following. Imagine you are a Soviet spy in the 70s, and you want to encode your message to your friends. So you want to generate random number key with which you want to encode it. And to solve this problem, you are given the certified random sequence by your favorite government in the form of a notebook. So you just open it at a certain page, get a random number, mark it up, and there you have it. So with pre-generated random numbers, you can get the key. Same applies here, and that would be one very highly inefficient extractor, but you can get certified random number, XOR it, and there you have it. The sequence that is definitely random because it contains the randomness of your source, and it is not the same, guaranteed to be not the same as the one from your notebook. Very inefficient. One thing that are you familiar with a guy called Von-Neumann? Von-Neumann, yeah. One very cool dude in information theory, at least. So he thought of the following. If we split this whole sequence into pairs, like this, we can map those pairs according to the following rule. So that's the table for Von-Neumann extractor. So we, according to this table, we map this to this pair to nothing, map this pair 1, 0 to 1, 0, 1 we map to 0, 1, 0, 1, and this to nothing. Hence, this sequence produces true random numbers 1, 0, 1. So that's that thing was proven to be absolutely correct with any distribution of your input number, input sequence. However, the drawback is that if you happen to have already a perfect sequence of equally distributed zeros and ones, then you will get random numbers, but it will be less than half of the numbers in the output than you have had true random numbers in the input. Okay.
So you loosen that.
So it is not very efficient in terms of information utilization. However, it's one very simple procedure, and no, I don't remember if it is used anywhere, because there is more interesting stuff. Another example of an extractor that is widely used, and most likely the one that is used here at the moment at least 3 times simultaneously now, is the following. So the problem is we get a certain sequence and we want to spit out random sequence. You must have heard about hash functions, right? So hash functions are the functions that are hard to reverse. We can get a value. We f of x easy f minus 1 f of x hard. So where f of x equals x. So those are so-called one-way functions that are hard to reverse. And the idea of hash-based extractor is the following: we take whatever input we get and feed it to a hash function. Hence, we produce a certain sequence that depends that will have equal distribution of ones and zeros, because that's the property of hash functions, of good hash functions. Okay. However, there's one problem. Can you tell what's the problem with this very extractor?
Always extracts the same thing. Always does the same thing. You get the same hash for.
Yes, exactly. So, in case we have one very weak source of randomness, a weak source of randomness is the one with very unequal probability distribution. Then we are very likely to get a lot of equal numbers, equal sequences that we feed to the hash function, and hence we will get equally distributed output, but it will not be uncorrelated. So this thing has a certain problem, and we have to get a certain value that may characterize this problem. So we must think of a certain criterion that will tell us whether this input and this output are good or not good for hash function. Okay, can we think of a certain criteria as for how do we pick the length of the input and the output sequences for our hash extractors? So basically, we can always say that if we get the very first number, it will most likely be okay. But if our sequences are very, very weak and are likely to produce, say, all zeros or all ones, then even getting one digit will not be secure and will not produce a good randomness extraction. So that's the question I'm going to address in the next part of our lecture. So we want to characterize what?
Sorry, we will be addressing the situation where those distributions are not constant in time. Because
that's one very good practical question, because it's a consideration that that bothers the creators of random number generators in real life, and they have to either prove that the distribution stays the same, or use something that has a certain degree of resiliency, like Von-Neumann extractor, that will work with any distribution at the cost of loss of information. Okay. Yes, that's a real life problem. Yeah, you're right. Okay, so the mapping problem and the weak sources. Super. Okay, so to get a certain intuition of what's going on and how to solve this problem, let us first try to do the following exercise. Imagine we have come to a D&D party and everybody forgot dice. So we want to get a D6 source, but all we have is a coin. We have E2. So how do we solve this problem? With a coin?
Roll 6 times? Or 3 times, so count more.
Okay, so how many times should we throw it?
3 times.
3 times, okay. We throw it 3 times.
No, it won't do the thing. You have to throw it 6 times. Plus 3 times. But then you can get 0. 5. Maybe 5 times.
5 times. Okay, so what will be the procedure? So let's say we got
No,
3 times is enough.
1, 1.
because we already have 8 possibilities and we can just drop 2 options.
For int. Magia for the.
Hungarian.
It says for int.
Yeah, Hungarian for me.
If you have 3, you have to do something with we have 8 possibilities, so we need to do something with 2 left.
Yeah.
What do we do?
Oh yes, indeed. So yes, first of all, it is indeed enough to throw the dice, to throw the coin 3 times. 0, 1, and 1. And how do we map this one into this? We want to get the number 1 to 6.
We can just use the mapping from all the variants to 1 to 6, and for 2 variants which are left, we can just repeat the procedure with some probability of repeating it several times.
Yeah, okay. You are absolutely correct. This. There's the table. So we are free to choose whatever mapping we want. So that be 1, 2, 3, 4, 5, 6, and better luck next time. Yes. So basically, what we see here is that 3 flips of a coin has more, let's call it power, more random power than 1 roll of a dice. One. Should have been 4. Anyway. Anyway, so there's one mapping. Let us think about another problem. In case we have, okay, just to make it clear, we have 3. D3. Can one imagine of a physical system with that has this property D3? My favorite one is the fly that is passing through the Mercedes-Benz logo, and it can pass through one of the sections. Okay, so that's our D3, and we want to map. Let's say D8. Example of a real life D8. That's so hard.
I'm sure there is a sided. You can do something like the same with not the Mercedes-Benz logo. It will be about the same code. Yeah. It's gonna work.
Yeah, I think you can just put glue 2 pyramids together.
Okay, yes.
There's like, it's called something like a tiger. No?
Yeah, nothing confirmed.
Exactly.
Here you go.
Cool. So how do we do this kind of mapping? D3 to D8.
The same way.
Yeah, absolutely. Now imagine the following. We have can we quantify what we are having here? Is there a mathematical way to describe whatever structure we have come to? So can we predict how many rolls of a certain die would we need to emulate a different die?
Oh, yeah, it's like in that case it's gonna be 2 and how
we just need to take seeding from logarithm.
Yeah, exactly. So basically, what we are doing here with this very structure, we have 3 rolls that result in 2 to the power of 3 outcomes. And the reverse operation is the logarithm, and hence the operation that gives us something that we have called the power, the random power of the event, is related to an operation of taking a logarithm. So, what is the value that logarithm, let's say 2 of what? So, what would we want to have? what do we want to get? So we cannot make logarithm of d6 because it's not mathematical. So.
Oh, of the number of states we need.
Number of states. Okay. Number of states.
Plus one mind.
Yeah, great. You are quite right. One thing that I want to mention here is that this thing breaks in the following case. Imagine we have some this interesting structure when the probabilities are not equal. So we have unfair coin, but we want to make a mapping to a fair coin. We have seen that there is one bad way in terms of information greediness, if you say so. That is Von-Neumann extractor. But what if we have, let's say, 1, 8, 3, 0, 3, 1, 7, 8, and we want just a simple D2 from this thing. Can we make something better than Von-Neumann has done? But considering the very same consideration, and to also characterize the power of this very event in a similar way that we have done to the Faraday. It's actually a hint is done like this. So can you explain?
So you basically take your unfair coin and you get you treat this as an 8-sided die. And you assign like the one outcome to basically, given your probabilities of 1, 8, and 7 8s, you treat it as an 8-sided die because it's a common denominator of your probabilities. And basically, you can know when the coin gets heads, it's your first outcome, and you can map for that. And if you get tails, it's any of the other 7 outcomes.
Okay, so you have done it better than I wanted to do.
Just go it a bunch of times.
Yes, so let me rephrase it a little differently. So the very informational power that we get from a certain event is described by logarithm of its probability. So we were talking about logarithm of the number of equally probable states, that is logarithm of 8. But if the states are not do not have equal probability, then amount of information is different for different events with different probabilities. Okay.
So if you get PO, that's more information than P1. If we get like PO outcome, so for instance, like on the less fortunate side, it's more information.
Yes, absolutely. So that's actually that. Okay, this thing is the definition of information. So congratulations. So this very power of events. Of random events is the information that contains here. That's something that Shannon and Von-Neumann like to do a lot. And for the events with unequal probabilities, the information is different, and we can see that this thing has more than 1 bit of information when we get this very unlikely event. So, frankly speaking, this very approach is the same that is used in physics, in statistical physics, to define entropy, because that's how people describe probabilities of the states of, say, molecules or whatever the agents in the systems. And you must have heard that entropy is the measure of chaos, right? So if we have the so-called chaos, that means that there's a lot of improbable little events that result in a lot of information that we need to know about system to describe it. The low entropy system is the one that can be described with very little amount of information, because there's little amount of states that the system can occupy. Okay?
So we went to compression.
Yeah, compression. That's one very good thing. Is it the following in the extractor, matrix multiplication? Okay. We will come to compression a bit later. So, with this very knowledge that amount of information is defined by probability, can we now move back a bit and now answer the following question? F of so how do we approach to solving the problem of our hash-based extractor? So what is the length of input? What is the length of output?
We don't know the distribution.
We know the distribution. Yes, here we assert that we know the distribution. And the distribution is unfair. So certain states are more probable than other states.
So we can just compute min-entropy and take the ceiling again of it.
Yes, absolutely. So let me repeat it in different words. So we, for a given hash function, we have a fixed number of output bits, right? Right. So whatever we feed, whatever length input we feed to the hash function, we always get the very same length of output. But we don't want to waste the resources feeding it too much information, hence losing the bits in the output. So we have to calculate the very minimal number of information that our distribution is capable to produce. Okay? Okay. So,
Maybe we can start with a real example with some sequence and compute an entropy of it.
Can we make it? Yes, we can. Cool. It would have been nice to do some live coding here, but well, not that good at live coding and live coding at all. So, let's say we have this very case 0, 1, 8, and 1, 7, 8. Can somebody calculate the information that corresponds to this very distribution? 1, 8, and 7. That was the homework. What is the logarithm? 1, 8.
-3.
Yes.
Yeah. We want information to be positive, so we're taking the minus. Yeah. Okay, and 7, 8. That's one. That is Arden. assistance.
It's long number.
Okay. With 0.1927 and
So,
so on.
cool. Okay. And something else. So that's the information of 0 and 1. Okay? And in our sequence, we have 0, 0, 1, 1. We can calculate information of this sequence, right? So it's just
Sum.
yes, exactly. Is it absolutely obvious why information of this string is just the sum of those guys?
Probabilities are independent. So
Absolutely right. So, when we are talking about information of string, it's sum of informations of the members of the string, because probability of a string is multiplication of probabilities of elements of the string, provided those are independent, and that's what we're talking about. It doesn't matter too much in case you are overloaded, but the point is the information of this string is the sum of informations of the element. So we can calculate it. We don't want an exact number at the moment. And for any string of any length, we can calculate whatever information there is. Can we calculate the average information? The average information for a string of given length n.
Is it like weighted sum?
Yes, it's exactly weighted sum, yes. Average equals you might have seen this very formula somewhere, and we will not use it. And what we are talking about, what we were talking about, is that any string will have a certain information associated with it that can be calculated, and we have this amount of information that is being produced, that should be being produced by our extractor, right? And we cannot produce more information than there has been in the input, right? It's just illegal. Hence, we may derive the limitation on minimal number of input string that is guaranteed to have this amount of information bits, right?
Mm-hmm.
So
if you have unfair input, the length of the string may vary.
we want to make absolutely positive that in any case we will have at least this amount. How can we do it?
So
guys,
really,
for a while.
we must go with the worst case scenario here.
Absolutely. What will be the worst case scenario for this very one?
All the ones.
All at once, exactly. So, let's say we have a hash function. What's your favorite hash function?
SHA-1.
SHA what?
SHA-1.
1. So, never fails. The length of SHA-1 output.
It's like what we're doing. I'm not sure.
I guess it is. Let's assume
a bunch of numbers. That's
L
should be
120. Okay. So for SHA-1 with 128 bits,
160.
60, 160.
160 bits.
160. We are scientifically correct. Our hash is extractor produces 160 bits of output. If our input is unfair binary distribution with 1878, how many bits should we feed to our extractor to be sure that there's at least 160 bits of information there?
we need to calculate the m, the amount of information we need. On
Then
that.
equals 160 times. But you have already solved this problem. So we have 160 bits of information in the output, and what is the length of the input that is guaranteed to have 160 information bits in it?
Is the input that has all ones.
Yes, and how many
So
numbers?
160 divided by this
By
0.19
Yes,
whatever.
Exactly. So 160 times 0.1927 to the power of 9.
The weight of the single symbol on the right is 1, right? Weight of the single symbol on the right is 1, right?
Yes, exactly, because those are random numbers, and with the true extracted random numbers, and this sequence has p equals 1/2 probability, and hence information equals 1 for any symbol. Yes, exactly, and maybe something else. Not here, but here.
Top.
Yeah, because n has to be integer, right? Cool. All right, so congratulations, you are already 1 month of learning randomness extractors. Fast. Cool. Let us do a little bit more of flexing and
What's the edge?
I'm sorry, I just have to mention that in my notes I have written this following line. So, what is the worst pickup line ever one can imagine? So,
That's like a bunch.
a man walks into a bar and says, "Hey, lady, so what's the logarithm of 1/8?" It's mathematically proven that in any case you will get a bad result. All right, so let's get some more examples of randomness extractors. Maybe you can come up with more of those, or having known all of this stuff. Just, we are solving the problem of mapping something random but not nice into something random and nice. So, go ahead. Can there be any more than what we have said?
It's hard to come up with.
Okay, yeah. Actually, it is, especially if all of those information is fallen apart. Okay. In the wild, there is a number of different extractors, and actually, those are dependent mostly on the requirements. As funny as it seems, as it sounds, it's not always optimal to use the most optimal extractor, because most likely you will be limited to certain conditions. Like, imagine you are an FPGA developer, and okay, imagine you FPGA. That's one very specific type of silicon hardware. That is, and basically it's an array of transistors.
Field programmable gate array.
So
you can program.
that's something where you program the hardware.
Yes,
So,
which is
yeah.
underneath.
In microcontrollers, you enter the microcode, and there is a certain architecture with all of those conveyors and stuff. And in FPGA, you program the very configuration, yes, the architecture of your chip. It is very fast compared to microcontrollers and microprocessors.
You mean faster to develop than engineer your circuit and put on silicon? You can prototype faster on FPGA.
It works a lot faster than what you can achieve with
Existing architecture.
with current general purpose processors and microcontrollers, because it can do only one task but very fast.
But it's not as fast as designing your own silicon, which is the
FPGA developers do need random numbers, and it is expensive to get a separate dedicated random number generator. So there are certain tricks that they do to basically emulate, if we know the hash function stuff, to sort of emulate the very same behavior of the system. So you have certain randomness that's flowing into your chip, and typically a typical example might be the inconsistencies of clock cycles, in case it tells you anything. It doesn't matter. You get certain random events with certain distribution, and you are limited to what operations you can do. So what they do is that they do a thing called shift registers with a feedback loop. So essentially, you take number 0 or 1, 0 or 1, and pass it to the next register, pass it to the next register, pass it to the next, and you fill your line of shift registers. And in certain cases, you also do feedback, let's say, with a plus or XOR. Typically, it is XOR because XOR table, XOR truth table has the same number of ones and zeros. And you can do this with with several cells, and the results will be sort of unpredictable, and it will be shuffled in a way. However, this thing is vulnerable in terms of pure maths. If we check the truth table, what numbers we map to which ones, it is very trivial and simple to do the reverse. However, that's something that exists in the wild because it does solve the problem good enough within the limitations that you have. And there are other ways to do so. So perhaps the simplest way to map a vector of length m to a vector of length n has studied linear algebra is just flash solution. We have a vector equals a matrix times a vector. I guess you are
Yeah, that's on this one.
familiar with this. In case you are not, you are familiar with this. Now, this thing is length n, this thing of length n, and this thing is of length n times n. And matrix multiplication allows you to use this very vector with certain predefined metrics to get a shorter or a longer vector. And basically this operation performs the very same thing that we have seen with hash function, but it is a lot easier to reverse it. However, it is also used in a while in certain applications where you are limited to what you can do with numbers, and especially it's good when you can generate this matrix with a certain seed as well. Okay, so this will be sort of pseudo-random, but based on true random, and with this very trick you will be able to get an extractor that will generate as much as